We learned about relative abundance so that we can use it to calculate atomic mass of elements, relative atomic mass of elements on the periodic table. So let's do a quick recap again. We say that elements are here, and this element contains atoms. It contains atoms, and then so atom 1, atom 2, and atom 3. And elements are what we see on the periodic table. And each of these atoms has their own masses. Remember, the atomic element is the same. Atomic number is the same Z, the same Z, the same Z, and then the same Z. Let me use an actual example to illustrate that to you all. And a common example that I'll be using is carbon again. So there are different lots of elements like that, but let's focus on carbon. So carbon is an element, right, of atomic number 6, and it has 3 different isotopes. So we have carbon 6 here again. Carbon with atomic number 6. They are all of the same family, so they all have the same atomic number. But here is 12, here is 13, here is 14. Even though they are all from the same family, they have different surnames. That's it. But same family name. That's the 6, right? So now the question is, if all these people are in this family, right, and they are weighing this, then if we take the entire family, what's the average weight of the family? Basically, that's what's the average weight of the family. So if you put all of them together, then what is the average weight of all of them? That's what we basically put somewhere here on top of the mother element. The mother element, right? So yeah, that's what we use mostly. Um, so that's what we are concerned with, right? Because first we look at how to we look at understanding relative relative abundance, how abundant each of these is in an element. Then we can use that to calculate the atomic mass of relative atomic mass of all the elements. Okay, so if you look on the periodic table, for example, let's focus on lithium. So if you look at lithium, lithium is having atomic number of 3. That's why it has position 3. Then you can see some mass over here, right? Some number over here, about 6.941. 6.941. So what you are seeing on the periodic table are the elements, and the number you are seeing there is actually the relative atomic weight or relative atomic mass. So is the average of the individual atoms in this element, like how we do it in carbon, right? Look at carbon. Carbon itself is 12.011, but it contains carbon 12, carbon 13, carbon 14. Based on the abundance of each of them, the relative abundance of each of them, coupled with their mass numbers, when we find the average of all that, we are going to have a particular number of this one. So this one is like the relative atomic weight of, if you put all the components or the contents together. So let's clean this and give us the formula. If you know the atomic weight and stuff, if you know the relative abundance of each of the isotopes, how do we calculate the relative atomic mass? The relative atomic mass, we are going to use formula A small r. So relative atomic mass of the mother element itself. We are going to use A small r. This will be equal to, so it's going to be atomic mass of, so atomic mass 1, right? That means relative abundance 1 plus atomic mass 2. That means relative abundance 2 of the second isotope plus atomic mass 3 plus relative atomic plus, then you'll be doing that addition for each of the isotopes until you get to the nth isotope. Until you get to the nth isotope, you do this. So you take each of the isotope, the atomic mass times the relative abundance of that particular isotope inside the sample. They will do that for all of them. When you're done doing the summation at the top, the sum of the products, and you come down, what you do is that you do relative abundance 1 plus, you sum we find the sum of all the relative abundances, then plus Rn. So this is a general formula that we are going to use in finding the relative atomic mass of the entire element, right? That's how to calculate the relative atomic mass of the entire element using the individual isotopes. And this is the general formula. We will look at relative abundance already, right? So the abundance is how each of the isotope, in which amount they occur in a particular sample for each of them. So we put all of them together, then we divide by the total abundances. Then, so this is a catch on this. If it is a fractional abundance, right? If it's fractional abundance, the sum of all these, should be equal to 1. If it is a percentage abundance, then the sum of all these will be equal to 100%, equal to 100. If it's a fractional abundance, then the sum will be equal to 1. If it is percentage abundance for each of them, the sum will be equal to 100. Enough of the talks. Let's go and solve some questions. We have chlorine consists of 2 isotopes. Chlorine 35 abundance 75.8 and chlorine 37 with an abundance of 24.2. Calculate the relative atomic mass of chlorine. So relative atomic mass of chlorine will be equal to, so let's take the first isotope. The first isotope of chlorine is 35. So it's going to be mass 35, right? Times the abundance of chlorine. That particular isotope is 75.8% plus the second one, 37. The mass is 37 times 24.2% again. So all divided by 75.8% plus 24.2%. You can see that if you add those in the denominator, you are going to get a total of 100% because the relative abundances are in percentages, right? So you do the product, the sum of the product divided by the sum of the abundances. So let's put this into our calculator and see. When I was done, I got the answer to be 35.484. Relative abundance has no unit, so there is no unit here. Relative abundance has no unit, so you don't add any unit at the end when you have a relative abundance, right? So we'll talk about something later, a relationship that will actually contain the unit, but this one will not contain the unit. The unit that we are supposed to have is gram per mole, but we'll talk about that later, right? Let's look at another example. Another example that we have, a sample of magnesium contains 3 isotopes with the following properties. So you have 3 isotopes of magnesium. So I'm going to say the relative atomic mass of magnesium will be, the mass of the first isotope is 24 times 78.99%, right? Plus 25 times 10% plus 26 times 11.01. So if you close this, you divide by the sum of all the abundances. Here the masses do not follow in this summation. So if you do this, we put this in a calculator again. So when I did it, I got 24.320, right? 3202. There is no unit, so you can stop at 2 decimal places and say you have 24.32%. So 3232, that's the answer, relative atomic mass of magnesium. Let's compare this on the periodic table. On the periodic table for magnesium, yes, so here this is actual periodic. This I'm seeing 24.305. Then for our calculation, you have 320, right? Yeah. So we are close. When we did for chlorine, we had 35.453 here, but then we our own we had something like 35.484. Okay, so there's a bit difference, right? In the next session, we'll look at another way of calculating the relative atomic mass, right? We have to look out for something. We have to look out for something. If not, we'll be getting it wrong. It's not always that it will just give it to us like this, right? To find the relative atomic mass. But we have to look out for something before we proceed with our calculation, which we'll cover in the next session.